Hello, everyone. My name is Shaun Crampton. I'm a distinguished engineer at Tigera, and today I'm going to talk about next generation observability and security with eBPF. So I'm going to start by kind of defining observability and running through the kind of pre-eBPF world, why you might want observability and what we mean there, and how security was done in the pre-eBPF world. I'm then going to introduce eBPF, the technology, and explain what it does and where it fits in. And then I'm going to go through the impacts on observability and security and kind of how it meshes the two together and how it all fits together at the end. So I think one of the themes is that eBPF tends to bring these two things closer together. So that's one of the things I want to draw out. Observability. What's the goal? I think what we want to do is we want to answer important questions about our apps while they're in production. So what is our latency for this type of request? Why is that API endpoint slow? Why did this database query take so long? Or which database queries are taking a long time in production? The reason we want to do that, we want to better operate and diagnose our applications. So in production, we tend to hit a range of problems that are very different to what we can test for in our test environments. So we have higher concurrency, we have things scaled out to multiple machines, we have to worry about problems such as many requests arriving at the service and contending for resources that are shared between multiple front ends, talking to multiple back ends, talking to multiple database nodes, things like that. Fundamentally, we want to we want it to allow us to improve our apps at scale, and we want to establish a feedback loop where we can tune the application, either by manipulating its configuration parameters. We want to then observe its response with our observability features, and then hopefully we improved it, and then we want to repeat it and improve it again. Maybe we'll go back and we'll add more observability features into our application. And I'm going to talk about what those might be in a moment. If we didn't quite get the information that we wanted, we might add some more. And then we go around the loop again. So we tune the app again, observe its response, and go on from there. So what might this look like in a real example application? If you look on the left there, I'm imagining here an application that's serving some sort of client requests. So we have a client all the way on the left, and the client isn't going to be able to get to our business logic, which is up in the top right, without going through the kernel and the network and all those kinds of things. So client makes some kind of request. Then we have a packet arriving at the kernel. The kernel's going to accept that packet, or maybe it's going to drop it if it was an invalid packet or something like that. Kernel's going to accept the packet. It's going to buffer it. And then it's going to at some point decide to push that up to the application, the business logic on the top right of the screen. Business logic is going to parse the packet, understand the meaning of that request, decide what to do with it. Then it's going to possibly do a file read or a database read. Maybe it's going to make a request to some back-end service, whatever. That will then loop through the kernel again. So represented that kind of just below the business logic there. And eventually it's going to decide what it wants to do with that request and respond. So then the response will go back through the kernel. And the reason I keep saying this will go back through the kernel is because that's going to be very relevant for BPF discussions later. But what might we want to do with this application to kind of make it more observable? Well, the key thing that we can do in the sort of pre-BPF world, and I want to emphasize, these are great things to do, BPF or not. We can add metrics and we can add tracing to our business logic. So metrics statistics. How long did this request take? How long do requests take on aggregate? Maybe we could calculate the quantiles, the 99th percentile and those kinds of things. Tracing. The key idea with tracing is to attach some kind of identifier to the requests that come in, and then we want to sort of propagate that identifier all the way through our application. So maybe the client has been given a session ID, and then the session ID would come in on the request. The business logic would then allocate a request ID as that arrives, and then you would have a log that gets traced out that says this session ID made this request ID, and then you would pass that request ID onto your backend service when you make your request over the network to that service, and so it can be passed all the way down the chain and then correlated at the end when you slurp up all those logs and blast them into your logging service. You get this trace of the request that goes through. That's all great stuff, and very high value. So the key thing there is you're instrumenting things that are personal to your application. So you can instrument exactly what you need and collect exactly the statistics that are relevant for your application. All great stuff. Downsides, when you want to add additional trace or metrics, that means a respin of your application. And if this is an application that's not really under your control, like some external application, third-party application you've brought in, you need to convince the developers of that application to add metrics and trace to allow you to observe what's going on inside. And the other thing is, well, what about all that kernel code? So a lot of the code that's running there is under our control up in the business logic, but there's a lot of kernel code there as well. So the packet arrives. When exactly did the packet arrive? That information can get lost. What's going on inside the kernel? How full are these buffers? Where's what contention's going on? All those kinds of things. The kernel can answer some of those questions. Each kind of subsystem in the kernel collects its own set of statistics, and there's tooling that allows you to access those. They tend to be very coarse, so maybe the TCP stack will record how many packets it drops because they had invalid checksums or invalid sequence numbers and those kinds of things. They're all spread out across the kernel, and if it doesn't record a statistic that you're interested in or a metric or a bit of trace that you're interested in, we're into oh dear territory. If you want to add something into the kernel in the pre-BPF world, you need to be writing a kernel module or submitting patches upstream to the kernel. For most enterprises, that's just a non-starter. We're talking a 18-month turnaround, assuming you can convince the kernel developers that it's something that they want to include, and assuming you have the expertise to be able to do that. Okay, so we'll leave that there for a second, and we'll talk about security in the pre-BPF world. And I'm mainly going to talk about kernel-based security features here. So kind of skipping over security at the application level, like TLS and certificates and things like that you might have in your application. So that's sort of out of scope for this. I'm more talking about the features in the kernel that allow you to lock things down, and there are lots of those. That's one of the main purposes of a kernel like the Linux kernel is to implement various security primitives. So you have security for each subsystem in the kernel, and sometimes multiple versions of those. Some examples might be IP tables for network security. So you can do things like block packets from certain CIDRs or allow packets from a specific allow list in an IP set. So Calico's IP tables data plane does that kind of thing a lot. If you want to secure syscalls, there are tools like seccomp, SE Linux for access control, and Linux security modules, and all kinds of other features in the kernel. The main thing to know about these is they're fairly fixed in what they can do. So They're all in particular places in the kernel, and they can only act within their little sphere of influence. The diagram on the right-hand side there is a diagram of the net filter, like packet path for handling packets. So this is where IP tables fits into the picture. So the little boxes with green tops are the IP tables, filtering tables and NAT tables and things like that. And every packet starts on the left of this diagram and goes through each of those stages step by step. And that's how IP tables works. You can't really change the order of those if it doesn't fit your application, and you can't really do anything different outside of that particular path. Same is true for the other technologies. So seccomp has its own way of working, and pre-BPF seccomp was a very kind of blunt instrument that could sort of disable all but a handful of syscalls. And to do that, you had to jump through a load of hoops. So you had to start with an application under your control, and then start the code you want to run in this kind of reduced privilege mode from that application, and go from there. Yeah, more mechanisms, similar sorts of ideas where you have specific things they can do or not. If you want a new mechanism, wherein to patch the kernel territory again, you're either needing to write some sort of module for the kernel, or get a fix accepted upstream. So that's the pre-BPF world. Let's talk about BPF. So what do I mean when I'm talking about BPF? Well, it stands for the, I believe, Extended Berkeley Packet Filter, but the name kind of leads you in the wrong direction. So it's certainly extended, and it certainly was based on the Berkeley packet filter, which is the mechanism that tools like TCP dump use to identify particular packets to dump when you run TCP dump. Or that's the sort of original purpose of it. But it's moved a long way beyond that. So what is it now? eBPF is a general purpose virtual machine that lives within the Linux kernel. So if you're familiar with things like the .NET virtual machine or the JVM, the Java virtual machine, it's kind of in that vein. So it has a bytecode like set of machine instructions that you can feed into it. And it has its own language for that, which is the eBPF bytecode. It's grown like far beyond where it started for network packet filtering. And there are now a whole range of hooks within the kernel to which you can attach an eBPF mini program. So where do you get an eBPF mini program? You write your eBPF programs in C, and then you compile them to the BPF bytecode language. You can then load those into the kernel and attach them to one of a number of hooks in there. There are hooks for a whole variety of things in the kernel, and more are being added all the time. There are hooks for network policing, various networking features. And Calico's eBPF data plane makes heavy use of those. There are hooks for tracing. So this is tracing in the sense of you get some kind of kick from the kernel when a particular thing happens, and then it's up to you what you do with that kick. So not exactly the same meaning of tracing as feeding IDs through your programs to trace them, but it's very closely related. There are also hooks for security features. So the seccomp mechanism that can be used to secure syscalls has been dramatically extended with eBPF. So you can do a lot more in that syscall, in that seccomp logic. And a key property of these that makes them very different from kernel modules is the safety is guaranteed of the eBPF programs. By compiling to a bytecode, which you can then feed into the kernel can process that bytecode, and it goes through a process called verification. And it verifies that the bytecode meets certain properties. In particular, it verifies that it can't crash, it can't loop forever, it can't corrupt memory it can't access memory that's outside of a particular range that it's allowed to access, and so on. Essentially, loading one of these programs in, assuming no bugs in the verifier, is very safe. Once the program is loaded into the kernel is then able to compile it further into real machine code for your particular CPU architecture, and that allows it to run very fast. So we call that just-in-time compilation. So the bytecode verified, just-in-time compiled, and then it's effectively running like it was a kernel module, but it's been proven safe before it goes into that mode. What can BPF programs do? One thing that they can all do is they can store information in BPF maps. So these are key value data structures that exist in memory inside the kernel, and you define them with your BPF program. So maybe you define a set of maps to store information about particular packets or particular sockets, or whatever it is that's your target of interest. And then the BPF program executes when it gets its kick, and it can store some information in the map. Then there are a lot of hooks that are read-only. So like the tracing hooks are mainly read-only, so they get a kick from the kernel when something happens. They can read the information that's associated with that kick, and then they can store it in a map or what have you. And then there are some hooks that have additional features. So the networking and security hooks, they can do a lot of things related to networking and security. So the networking hooks can drop packets, or they can add headers to the packets, or they can manipulate the packets. For example, doing NAT on the packet to load balance it or something like that. And Calico's BPF data plane does all of those things. The security hooks usually have the capability to just deny whatever operation was attempted. Deny or change the scope of an operation or something like that. So you have your read-only hooks for tracing and your more advanced hooks for networking and security. A key thing that BPF gives, like across the board, is it unlocks innovation. So in your networking hook, you can do something that the kernel just couldn't do with network packets before. So in Calico's BPF data plane, we do a type of encapsulation that the Linux kernel doesn't support in order to implement Kubernetes node ports, for example. We were able to add that in. We can send packets on a path that they just wouldn't go otherwise. That's kind of something that's across the board. So all of these hooks, you can do things that no one had thought of when the kernel was written, and that's really powerful. Okay, so let's talk about eBPF and introduce that. So what is eBPF? And how does it differ from what's gone before? eBPF is a technology in the Linux kernel. It's a virtual machine technology. So it allows you to load a bytecode program from user space into the kernel and attach it to a hook in the kernel. So BPF programs are always attached to a hook, and that means they get triggered when something happens. They don't kind of run on their own. What does it mean to say it's a virtual machine and bytecode and that kind of thing? Well, if you've come across the Java virtual machine or the .NET virtual machine, it's a very similar idea. By compiling the code to a bytecode instead of directly to machine code, we get an intermediate sort of form of the program that we can do more processing on. And in particular, the Linux kernel has a verifier that takes the BPF bytecode program and verifies that it's safe. Unlike a kernel module, when you load a BPF program into the kernel's able to inspect the BPF program and make sure that it's safe. It can make sure that it can't crash, it can't loop forever, it can't corrupt memory, and a host of other like safety guarantees that mean once it's loaded into the kernel itself won't be disrupted. And the worst thing that can happen by loading a BPF program is you slightly slow down some operation, or if it's a BPF networking program, maybe the program is bugged and it blocks the wrong packets or something like that. But we have this really nice safety guarantee. And then once the program is guaranteed safe, the kernel is then able to compile it further into real machine code. So it runs at full speed, just like a kernel module would. So you get this very fast way of attaching small mini programs into your kernel. I skipped over the types of hooks that we have in the kernel. There's a very wide range. There are hooks for networking operations. So things like sending and receiving packets in the kernel, those can be hooked. And those hooks are very advanced and they have lots of features. So the BPF programs attached to those hooks can do things like dropping the packet, adding an extra header onto the packet and forwarding it somewhere else. Kind of interesting networking operations. Well, if you're interested in networking, which I happen to be. And the Calico eBPF data plane makes heavy use of those. So we do things like adding extra headers onto the packet in order to forward them over a VXLAN tunnel, inspecting inside an ICMP packet and reversing the DNAT inside the packet and things like that. So we can do quite involved things in the networking hook, and we still have to pass the verifier. So the program is still guaranteed to finish, and it's guaranteed to not corrupt memory and that kind of stuff. The worst we could do is break the individual packet if we got our logic wrong. There are other hooks. So I mentioned here there are read-only tracing hooks everywhere in the kernel. And the kernel basically allows you to attach a BPF program to almost any function inside the kernel. And I mean kind of subroutine function inside the kernel. And that allows you to inspect the arguments of the function. Then what you can do is you can take it and save it off into a BPF map. So you could save off some information into a BPF map. BPF maps are kind of key value data structures that we can keep inside the kernel. They're totally, self-defined what they mean by the BPF program. But the nice thing is BPF programs can share them. So you can have different programs in different parts of the kernel that share a map. And you can also read them from user space. So this is a key kind of communication vector to get information up into user space and make it useful. There are also security hooks available. So the security hooks can do things like police syscalls that programs make. So syscalls are the interface that user space programs have to the kernel when they want the kernel to do something. Most programs will make hundreds of syscalls per second, or maybe they try to make kind of a bit fewer than that, but they make handfuls of syscalls per second, and you can police what happens when those syscalls are activated. So usually the kinds of capabilities that a security hook would have would be to just prevent an operation, and then an error would be returned to the application. So you could police the opening of files. I think that's a fairly common thing that people do with the security hooks. What's the key benefit of the eBPF approach? I think it unlocks innovation. So you don't have to wait for the kernel to be updated to add a new feature. You can do lots of read-only operations on the data that the kernel's manipulating, so you can get very deep information about what the kernel's doing. And then for the things where you're allowed to make kind of write operations like the networking and security hooks, you can be very creative about what you actually do in those hooks, given the features that they're capable of doing. So what might observability look like once you have eBPF in the mix? First, I just want to emphasize, you probably still want to instrument your app if you can. That's still very powerful. That's how you can get the metrics that are really key to your particular app, and that's how you can plumb tracing through. Unfortunately, I don't think anyone has cracked magical BPF tracing yet and got tracing request IDs all the way through without requiring some kind of proxy or something to be inserted. But you can use BPF to insert a proxy, which is an interesting use case. eBPF really lets us get a sort of X-ray view of the things that are going on in the kernel and add those into the mix for our observability and tracing. In the example I've given here, a packet arrives. Well, if you're running the Calico BPF data plane, that means a BPF program gets activated at that point. In that program, we get all kinds of information about the packet. its size, who it's going to. We can look up the socket that it's going to be processed by. We can get the process ID of the application that it's going to be processed by. And we can save off any kind of subset of that information into a BPF map or send a message directly to a user space program to handle it. Then it's going to be delivered to the application. Well, we could hook that point. We could figure out how full the buffers are. If the buffer's got full and the application's not handling it, we can store off information like that. Then we get into the business logic. There we're into user space. Right now, I don't think there's big support for eBPF in user space, but that is sort of something that's going on as experiments at the moment. So particularly Golang programs can be instrumental with eBPF to some degree. Then once we get back into the kernel and we're making that, file read, or we're reading from a backend service, then we can hook that again. We know what file we could record, what files are being read, and try to correlate that with slow requests, that kind of thing. And then eventually the response is going to be made by the application. Again, we get more opportunities to hook those. So BPF doesn't kind of obviate the need for metrics and tracing in your application, but it allows us to get a lot more information out of the kernel, and it allows us to iterate on the information that we want to get out of the kernel. So if this isn't quite the right amount of information, or we're not getting quite the right information, then we can spot that, and as part of that feedback loop that we have, we can change what we record without needing to switch out the kernel. Let's talk about security a little bit. I feel like there's a couple of strands here. So one strand is there are a bunch of features in the kernel, security features, that are using eBPF as a kind of core aspect of the feature. There's all the network-related eBPF hooks, which the Calico data plane and others are using for their network security features. Going through some of those hooks, we've got the XDP hook, which is very interesting because it can be hardware offloaded for super high performance. So in Calico, we've used that for denial of service protection. Even back when we had our IP tables data plane, we kind of layered this on top. So the XDP hook it can run all the way in the network card as soon as the packet arrives and before the CPU of the computer even gets involved. So that can be super powerful for blocking like huge volumes of traffic very quickly. Then we get to the next hook, which is where Calico's eBPF data plane lives. That's the traffic control eBPF hook. First of all, it's advanced enough to implement the same suite of features that we had in Calico's IP tables data plane. But we can also do a lot more that we couldn't do before. So in particular, we can do things like custom encapsulation to be able to preserve the source IP of incoming traffic. So that kind of loops back into observability territory as well. So you have a packet that came into a Kubernetes node port, for example. Rather than SNATing that packet, which is what kubeproxy does in Kubernetes in order to get it to a backend service, we can encapsulate it in a custom way and send it directly to the host that is hosting the backend pod for that service. And that allows us to preserve the source IP all the way to the backing pod. Now that's really nice for your ingress server logs and things like that. It preserves that IP all the way through to your your ingress nginx or whatever it is that you have there. The key thing there, is that just that ability to innovate. So we can do that creative endcap that would have taken years to get through the kernel process, and then we can change it up and do it slightly differently if a more advanced load balancing algorithm or something comes along later. Another feature, so syscall policing with eBPF setcomp. So I believe Google Chrome's process sandbox is based on this. So Google Chrome is I'm sure everyone's familiar with, is a web browser, and it runs a lot of code in its virtual machines, like JavaScript virtual machines, that's come from outside. And they're very worried about, what if there's a bug and someone breaks out of this layer of protection? How can we layer on another layer of protection? So people who want to go from a web page to root on the host have to fight through, layer after layer of protection. And one of the layers of protection they have is they sandbox their whole process so that the process is very limited in what it can do at that kernel user space boundary. So it's only allowed to make the system calls that Google know that Google Chrome needs to do in order to proceed with its normal operation. So if some user code running in that JavaScript virtual machine somehow breaks out of that layer, it still can't do any new system calls that it wasn't able to do before, or that the browser wasn't able to do. It just reduces the attack surface there. Something that's recently gone in, Linux security modules. So these allow you to implement mandatory access control for files and resources. Not something I'm personally familiar with, but I was just checking to see what had gone in recently on that front. So yeah, one theme of security with eBPF is there's just new features that are unlocked by eBPF, and I think we'll see a lot more similar features being added that will use eBPF where they need that customization of the feature. We'll see a lot of that going forwards. But I think another aspect to the story is we'll also see these two things of observability and security kind of converging slightly. So observability is about kind of that feedback loop with you to tune your application, but there's nothing stopping you from using eBPF features to have tighter feedback loops that implement security and things like that as well. So I think eBPF is kind of becoming this lingua franca within the kernel where all kinds of different features and different hooks are using it. And there's nothing stopping you from taking a hook over here and writing to a BPF map to, get some piece of the puzzle and store it off. And then when you have a hook over here that's triggered, it can look in the BPF map to see, to influence its decisions. So while we might want to be collecting all this information and streaming it somewhere to kind of get observability in our application, it's also very powerful from the security point of view, because maybe you have a hook over here that's grabbing the identity of the application as it makes some requests to the kernel, and then later on you have a network packet arriving, and you can correlate the two and ask yourself, should this application receive that network packet with the details from both domains? And that's really nice. Further back, you can do things like track file system calls. If you see file system calls that are modifying a binary and then the binary gets run, that's the kind of thing that you can detect, and people are working on things like that. You can verify the binaries. So maybe you calculate the hash of the binary before you allow it to go and make a network call, that kind of thing. And something that we've experimented with as well is working on anomaly detection. So this gives you richer information to feed into your anomaly detection framework. So you have this kind of rich observability sort of security information that's feeding into your anomaly detection as well. And all of this, because it's eBPF, because it's kind of inserted into the kernel at runtime, you can iterate on it as new threats and new ideas arise without having to update your kernel. So I think that's where this is all going. Very rich kind of soup of information we can extract things from and then feed them into observability, feed it into security engines, and then also close the loop and do enforcement as well on certain operations. So that's the end of my talk. My name's Shaun Crampton. I'm a distinguished engineer at Tigera. Thanks very much for your time, and hopefully you've learned something about observability and security with eBPF. Thanks, everyone.